Derek is a student of Richard Ward. He's in Leeds now. He used to be in Durham as a graduate student and undergraduate in work. Apart from being a student of Richard Ward, he's got very good students himself, Josh Cork. So he's doing his generational work. So good luck, and let's listen to him.
Okay, thanks very much for the introduction, and thanks for having me here for a week. It's been a very stimulating week I've been here, so you've all made me feel very welcome. As intended, this picture prompted a few discussions before the talk started. So
I just have one slight thing. I know I'm getting old, but I don't think it's July.
Oh, yeah, okay. I reused the slides from, yeah, I changed the future, but not the date. Okay. I'm sure that's not the last typo that we'll see.
I guess what you do is you come again in July, and then this could be the first slide of a new talk.
Okay, yes. Now I've made my commitment to come again. Yeah, so on Tigran's recommendation, I went to the Chester Beatty Museum / library on Tuesday, and this is one of many wonderful things that I saw. So this is it's a very tiny thing. It's sort of like an ornament that you would carry around with you. It shows a horse coming out of a gourd. A gourd is a kind of a type of fruit, for example, a squash or a pumpkin or a cucumber. And according to the caption in the museum, there's a saying in Japan, a horse has come out of a gourd, and that means something unexpected has happened.
It's happening here. You are Japanese. Do you know that saying? Can you say it again for some?
A horse has come out of a gourd. No. Okay. This was an item from 1 or 2 centuries ago, so maybe the saying is not common anymore. But I wanted to show this picture both because I like it and because this is a talk about something that unexpected that has happened. So Tigran told me not everyone here would have seen monopoles before. This is a talk about monopoles. So I thought I'd spend quite a bit of time filling you in on some of the 50-year history of the study of monopoles, but by no means all of it. But it starts with the work of Tuft and Polyakov, 1974. So they were looking at a Yang-Mills-Higgs theory where you have an SU2 gauge field and an SU2 adjoint scalar, phi, and you write down this fairly natural-looking Lagrangian with a symmetry breaking potential. And then you look for static solutions with finite energy. And if you want the energy to be finite, then the potential term had better go to 0 as you go out to spatial infinity. So that gives you a boundary condition that the length of phi goes to p as you go out to infinity. That has 2 interesting effects. The first effect that has is that this non-zero vacuum expectation value for phi breaks the gauge symmetry. So at infinity, the gauge symmetry is broken from SU2 to U1. And the second effect it has is it brings topology into the system. So imagine taking a very large sphere around infinity, That's one copy of a sphere. And then this condition that the length of phi equals p, well, phi lives in a three-dimensional Lie algebra, so that condition constrains phi to live on a two-sphere. So then the map phi living on this very large two-sphere near infinity is a map from S2 to S2. And if you look in a topology textbook, you'll see that any such map has a winding number. So that's an integer that sort of characterizes how many times the phi wraps the two-sphere around itself. So you have this system where there's some topology and there's a gauge group broken to U1. And then what both Tufte and Polyakov did independently, they looked for spherically symmetric solutions of the equations of motion. This is just doing classical field theory. So write down the Euler-Lagrange equations and try to solve them. And they both found this solution. And the interesting thing about the solution is if you look at the magnetic field near infinity. So I told you that near infinity, the gauge group is broken to U1. So then you're effectively in an electromagnetic theory. So then you can write down a formula for the magnetic field. That's B. This is the formula. You're just sort of projecting. You're projecting F onto the direction given by phi, and they observed that asymptotically that has this simple formula. It looks like xi over 2r cubed. Oh. So if you remember your electrostatics, that's the formula for the electric field induced by a point electric charge, except here it's not an electric field, it's a magnetic field. So this solution that Tufte and Polyakov found from very far away, it looks like a magnetically charged particle. Okay, and hence the name magnetic monopole. So that's what they did, and that was exciting because magnetically charged particles had been hypothesized for a long time, and this was the first time someone had been able to find one in a conventional looking field theory. Okay, so in this setup, you have this solution due to Tufte and Polyakov. It has winding number 1, and there's no solution with winding number bigger than 1. Well, that's because this solution looks like a particle with magnetic charge. If you try to put together two solutions with the same magnetic charge, they will repel. So that's all there is to see in this model. Okay, a year later, 1975, Prasad and Summerfield were looking at the same system and the same solution, but they took the limit where the coefficient of the potential goes to 0. So you no longer have a potential forcing the length of phi to equal p, but you can still write down a solution where the length of phi tends to p at infinity. That's what they did, and the Tufte-Polyakov solution persists in that limit. That there's still a monopole there, and special things start to happen. So they didn't notice this, but Bogomolny noticed this. If you take this special limit where the potential disappears, the Euler-Lagrange equations, the equations of motion, reduce to first-order equations. So normally for field theory, the equations would be second-order. In this limit, you have a first-order set of equations and anything that solves those first order equations is an absolute minimum of the energy. There's a sort of simple argument that the energy is always bounded below by a constant, and it hits that bound exactly when this equation is solved. And the other special thing that happens in this limit is the long-range fields involve not just a magnetic field representing the magnetic charge, but there's also a scalar field. So these Prasad-Sommerfeld solutions carry both a magnetic charge and a scalar charge. And now think what happens if you put them together. Well, you have two of these monopoles. Their magnetic charges make them repel, because like charges repel in electromagnetic theory, but their scalar charges make them attract. And the magical thing is that those forces exactly cancel if you do the asymptotic analysis. Okay, so you can start thinking about solutions with n bigger than 1, and it turns out there are lots of them. So what's now known is that for a given topological charge n, there's a whole manifold of solutions of this equation. It's a manifold of dimension 4n. There's a simple explanation what, it's an index calculation that tells you the dimension of this space. There's a simple explanation. The simple explanation is, well, you think of a charge n monopole as being made up of n charge one monopoles. So each of those charge 1 monopoles has 3 degrees of freedom describing its location, and then there's 1 extra degree of freedom, which is a kind of internal phase parameter. Okay, so where are we next? Oh yeah, and something to note for later. So the Bogomolny equation, this first order equation, it's a very special equation. And one of the special things about it is it's related to the self-duality equation in 4 dimensions. So you can take your monopole gauge field and interpret the scalar phi as an additional component of the gauge field, and then asking for the monopole to solve the Bogomolny equation is the same as asking for this 4-dimensional gauge field to have self-dual curvature.
So in that picture, the scalar charge is an electric charge.
Sorry?
In that picture, the scalar charge is an electric charge. It's just E. The phi is A0, that's a potential for electric fields.
Yes, except, I mean, I've been working in a Euclidean signature space-time, so yeah, something like an electric charge, but it's sort of in imaginary time. Okay, so that's the story of static monopoles, and there's a lot I've not told you this. Those equations are integrable. There's all sorts of clever techniques for constructing the solutions, which we won't go into. What I'm going to tell you instead is I'll tell you a bit about dynamics. So going beyond just the static solutions, what do we know about the dynamics of monopoles? So Nick Manton was the first person to think seriously about monopole dynamics, and he came up with the following idea to approximate the low energy dynamics. So what he said was, we know the moduli space that describes the things whose energy is at an absolute minimum. That's like the minimum of the potential energy landscape. So if you have slowly moving monopoles, what you would expect them to do is they'd sort of just wander around, staying very close all the time to this minimum of the potential energy landscape. So that's known as variously as the Manton approximation or the moduli space approximation to monopole dynamics. Okay, so let's look at that in a bit more detail. So suppose now I have A and phi, and I'm going to say they depend on t, and for every time t, A and phi are still in the moduli space of monopoles. So I'm going to call their velocities little a and little phi. And because A and phi solve the Bogomolny equation, little a and little phi solve the equation I've written here, dA phi plus a phi. That's the linearization of the Bogomolny equation. That's satisfied just because they solve the Bogomolny equation for all time. But then remember, this is a gauge theory, so I could take a path in the moduli space, and then I could make a time-dependent gauge transformation, and it would look like a different path. And if I did that, the velocity vectors would get changed in this way. So adding on something to A and something to phi that depends on this gauge transformation parameter chi. Okay, so that creates that creates some redundancy in how I represent this path. And the way to fix that redundancy is to impose one extra condition, this Coulomb gauge condition. So that the first term there, that's just the divergence of little a. I've written it in mathematical notation, but it's just the divergence and then commutator of phi with phi. In Manton's formulation, that condition arose as Gauss's law. So there's one of the equations of motion for the system is Gauss's law, and if you write it down in this language, that's what it looks like. And then, so then the kinetic energy for this time-dependent monopole then is just given by the integral I've written there. So integral of AJ, that's for I guess that's the electric energy, and then term involving the derivative of phi. And you can take that and interpret it as a metric tensor, if you like. So this puts a metric on the moduli space of monopoles. And Manton's observation was that geodesics for that metric approximate the dynamics of monopoles. Okay, so that was from Manton. That was just a sort of proposal, an idea. But Stewart in 1994 proved that as a mathematical theorem. So now that's something we really know is true. Okay, and yeah, we're still back in history. So that was the start of the 80s, and by the end of the 80s, people were able to use this to simulate monopole dynamics. So this is a famous video which was made, I think, about 1990-ish. People at IBM were involved with it, and this is showing you a little bit of dynamics of monopoles, and all of this was produced using Manton's moduli space approximation. So I'll shut up for a minute. So yeah, this is dynamics in the moduli space of two monopoles. So you're starting with two well-separated monopoles, and then they're approaching with an impact parameter, and as you can see, that as they get close, that they have an influence on each other. So the very interesting thing is what happens if there's no impact parameter. And for people who know about this, this is now quite famous. So if there's no impact parameter, they approach and they scatter and they emerge at right angles. And there's a sort of there's an explanation for that. It's to do with the fact that these two monopoles, they're indistinguishable, right? I started with just a scalar field, and then the two monopoles, well, they're both zeros. I can't tell which is which. So somehow, because they're indistinguishable, they can't decide which way to go, and so they make a compromise and go right angles. Anyway, we don't have time to watch all of this, but I thought it would be.
Has anyone ever solved the equations of the system without the approximation?
That's an excellent question. So just in the last few months, there's been a paper from a group at Munich where they have solved the system using a proper numerical methods for full simulations of fields. And I mean, not surprisingly, they look the same, but they did notice a few differences. According to that paper, that was step one, where they wanted to test their algorithm by reproducing what was known, and then they're planning to go to high energies and look for more interesting stuff later. But yes, so the answer is yes, but surprisingly, only in the last few months, people have started trying to do that.
Just presumably there's nothing that prevents 4 from coming out instead of 2.
Well, so in this system, there's a sort of conserved topological charge that tells me the number.
But it's 0, isn't it?
No.
It's not a monopole and anti-monopole.
No, this is a monopole and a monopole.
But you could produce monopole and anti-monopole fields. Yes.
Right. Yes. Okay. So, I mean, that's a different game entirely. Actually, that's another kind of simulation that has done. So, R2 Ratanji, for example, I think he's one of the people who's been looking at collisions of monopoles and anti-monopoles.
But you could look at a collision of 2 monopoles and you get 4 out.
3 monopoles and anti-monopoles.
Oh, okay.
It's purely classical.
Yeah, no, it's purely classical.
Yeah.
Because I don't see why you couldn't.
Yes, but
if you hit it hard enough.
Right, but you have to hit it hard enough, and you have to think. So to produce anti-monopoles from monopoles, I think you need to get your aim right as well. It's kind of from the, I mean, at least for what people have tried for a long time is to produce a monopole anti-monopole pair from radiation. That's pretty difficult. It can be done, but it's difficult. And so, yeah, I imagine that, but yeah, I don't doubt that people are interested in trying to do it. But yes, that's high energy dynamics. So this old school stuff that I'm talking about is low energy dynamics. Okay, let's get back to talk. Okay, so done that. Right, so a bit more about the story behind that video. So that video was produced by finding geodesics for the metric on the moduli space of charged 2 monopoles. Well, to be able to do that, you do need to know the metric on the moduli space of charged 2 monopoles. So the people who found that metric were Atiyah and Hitchin in 1985, I think. And actually, they found the metric explicitly. special achievement. And the way they found the metric was by a ingenious indirect metric. So by that time, they knew that the moduli for any charge, the moduli space of monopoles is a very special manifold. It's a hyperkähler manifold. So hyperkähler manifold means you have three complex structures, I, J, and K, and they satisfy the relations of the algebra of quaternions. So I squared, J squared, and K squared are -1, and IJ is equal to K. I thought I'd put those up because I think next week you're having, in Dublin, you're having some commemorations for Hamilton's work. So nice to see those. Anyway, that was really important for Atiyah and Hitchin's calculation. So rather than sort of trying to calculate the metric by brute force, they said, well, we know what symmetries we expect it to have. We know it's going to have this hyperkähler property, and that information, and we know what the global topology will be. And combining all those bits of information, picked out a unique metric, and which they were able to write down explicitly. And that's a very famous metric now. Well, I'll say more in a minute. More other stuff that people have done with the metrics since the video. So the video is showing you the classical dynamics of monopoles. You can also use the moduli space metrics to study quantum dynamics of monopoles. And you can do both regular quantum mechanics and supersymmetric quantum mechanics. Sen was the person who made the biggest impact on the study of quantum dynamics. So he observed that there was a duality relating monopole dynamics with something else, and from that duality, he was able to make predictions for the supersymmetric quantum mechanics of monopoles. In mathematical terms, those predictions, well, they say that there should be certain bound states of monopoles, and they would show up as, well, not as a wave function on the moduli space, but a sort of wave function that takes values in the space of P forms. That's the right kind of setup for this particular kind of supersymmetry. He sort of made predictions. Well, yeah, he made predictions about the quantum supersymmetric mechanics using this duality, which then became mathematical conjectures. There's been a lot of work on those since then. So Sen's conjecture for two monopoles was proved again by Hitchin in 2000. Sen's conjecture for three monopoles was proved by two people in the US, Chris Kopke and, his collaborator's name has escaped me, so sorry if you're watching. And Sen's conjectures for 4 and beyond are still open. Okay. Another thing that's come out of this study is the classification of gravitational instantons. So the Atiyah-Hitchin metric on the space of charged two monopoles, that's one example of a gravitational instanton. So when I say gravitational instanton, for this talk, I mean a four-dimensional complete hyperkähler manifold which solves the Einstein equation. So that means it's Ricci flat. So people were interested in those things before. Gibbons and Hawking were the early proponents. Yeah, Atiyah-Hitchin's metric at that time was an interesting new example of a gravitational instanton. And since then, many more examples have been discovered, and there's now a very good understanding. So they're classified into these 4 families: ALE, ALF, ALG, ALH. Within each family, there are different types. There are A types, D types, and E types. And recent work of Chen and Minerve and other people has given us this quite complete picture. So one thing that Sergei Cherkis is doing at the moment, he has a program of monopolization. What he's trying to do is realize all of these known types of hyperkähler manifolds using monopole moduli spaces. So the Atiyah-Hitchin, that's one example of an ALF. We know that arises as a monopole moduli space. Cherkis is trying to realize all of the others, and the benefit you get from this is you learn about the relations between the different types of gravitational instanton, how to go from one to the other by varying the parameters. Okay, and then this is one picture from one of his papers. So each of those diagrams represents a different monopole moduli space that's creating a different gravitational instanton. Okay, so that's a bit more about what's happened with metrics. Anyway, this talk is about really about new work on hyperbolic monopoles. So everything I showed you so far, that was monopoles on Euclidean space. But you can, if you wish, replace Euclidean R3 with any other Riemannian 3 manifold. And well, if you replace it with the 3-sphere, there are no solutions. So the next interesting thing to try is replace it with hyperbolic space. So here I've written the hyperbolic metric. I'm using the upper half plane coordinates, also known as the Poincare upper half plane model, or upper half space, I should say. And the monopole equation, the Bogomolny equation, looks exactly the same, except this star now it knows about the metric. So if I wrote that in components, it would look slightly different to the equation we saw before. The boundary condition is still the same, so I still ask for length of phi to be equal to p at infinity. Where is infinity here? So the boundary of hyperbolic space is a 2-sphere. In this model, it's the plane where rho equals 0, together with one more point at infinity. And then the interior, that's where rho is greater than 0. So the first person to think about monopoles in hyperbolic space was Michael Atiyah. And what got him started thinking about it was a realization that hyperbolic monopoles are again related to self-dual connections in 4 dimensions. So whereas with monopoles on R3 that they correspond to self-dual connections of invariant translations, this time you get self-dual connections on R4 invariant under rotations. So you can kind of see how this works by writing the metric on R4 in polar coordinates. If I take the metric on R4 and I do polar coordinates for 2 of the 4 coordinates, then I get something like what's written on the left. And then if I just divide by rho squared, so make a conformal rescaling and expand it out, I get d theta squared, that's the metric on the circle, plus the metric on the hyperbolic space. So then if I put my hyperbolic monopole together as a 4-dimensional gauge field, make phi equal to the theta component, then that gives me a connection, and yes, and the basic fact is self-dual equation for that connection is the same as the Bogomolny equation for the monopoles. Except here you have one extra fact here that helps. So here, if you start with a finite energy monopole on hyperbolic space, the instanton will have finite action, and that's good because for a long time people have known how to construct instantons with finite action. There's something called the ADHM construction and various other techniques. So the correspondence is a bit more helpful. But there's a catch. So this correspondence only works when p is a half integer. That's because you kind of you have to make sure that the connection closes up properly at rho equals 0. To make that happen, you need to choose the boundary condition correctly. But you can talk about hyperbolic monopoles even when that condition isn't there. It's just when it is there, it helps. Okay, so it's been known for a very long time that while you can do hyperbolic monopoles and that you use things like the ADHM technique to construct them, one thing that doesn't work well for hyperbolic monopoles is you don't get a moduli space metric. So in many other ways, hyperbolic monopoles are mathematically nicer than Euclidean monopoles, but this is one case where they don't seem to behave well. So I claim that the metric that we wrote down before is ill-defined if we do it on hyperbolic space. So here's the argument why, and it has to do with the holographic property of hyperbolic monopoles. So if you've done anything with ADS-CFT, you'll have seen something similar to this. So if you have a hyperbolic monopole, it leaves an imprint on the two-sphere at infinity. There's a electromagnetic field on the sphere at infinity, and that determines the monopole. So that means whenever you move the monopole in any way, that changes the imprint in infinity, and so the impression in infinity fully determines what the monopole looks like in the interior. Okay, so in some cases, holographic properties are conjectures. This is one that has the status of a mathematical theorem. Anyway, the significance for us is it makes the metric a mess. So if I do what I did before, I take a path in the moduli space of hyperbolic monopoles, and then I let little a be and little phi be the velocity vectors. I know because of this holographic property that little a has to be non-zero on the boundary of hyperbolic space. And so then I try and write down the kinetic energy, the integral that gives me the metric. It looks something like this. I've got rho squared, ax squared, ay squared, a rho squared, and then there's a 1 over rho cubed in the volume form. So in that integral, altogether I've got d rho over rho, and that's a divergent integral. The only way it could be vanished, the only way the integral could be finite is if the other bits went to 0 as rho goes to 0, but the holographic property means they don't, so it's a divergent integral. So that looks like it's killed the idea, right? There's no metric, so nothing more to say. In spite of this apparent difficulty, lots of people have tried creative ways to put metrics on the moduli space by other means. So this is a very brief history of that. There's one sort of body of work using twistor theory to create metrics, or at least geometric structures. That started with Hitchin in 1993. He wrote down some quite famous self-dual Einstein metrics, continued by his student Oliver Nash, who is Charles knows very well. Then Roger Belaski, Lorenz Strachhofer took Nash's work a bit further. So that body of work is mathematically very nice, but the connection to the physics of monopoles is not at all clear. So for example, these Hitchin metrics, if you take them seriously, they predict that if you take, as two monopoles move away from each other, they accelerate very rapidly and they will reach infinite separation in finite time, which is doesn't sound like a very plausible picture of motion. Okay, there's also been some work of Jose Figueroa, O'Farrell, and Garanti. I didn't put the date, that was 2016. So they looked at the supersymmetry of hyperbolic monopoles. Another idea, apparently this was Michael Attia's idea, so you can get a finite metric on the moduli space by using Attia's conformal rescaling. And that's a nice metric, but the trouble is it breaks some of the symmetry of hyperbolic space. So it's a metric, but it doesn't have all the symmetries you would expect for motion of monopoles on hyperbolic space. So that's definitely not a good picture of dynamics. Recently, Paul Sutcliffe has been looking at what he calls the boundary metric. That's sort of basically renormalizing that divergent interval. And that does have a close connection to monopole dynamics, it would appear, or at least he would argue. But the trouble there is, well, it's not mathematically very elegant. There's a metric and it can be written down, but it doesn't seem to have any of the magical properties, nothing like hyperkähler, for example, that we saw for monopoles. And one other thing that's been done, so Gibbons, Warnick, and Franchetti Ross, took a more pragmatic view rather than talk about monopoles in general. They tried to just write down a metric that describes the motion of well-separated hyperbolic monopoles. And the interesting story there was they recovered a metric that's known as the hyperbolic tag nut metric, previously studied by Claude Brugren. So that's nice, but it doesn't describe what happens to the monopoles when they're close to each other.
You've written L2 metrics on S4. S4 is not negative Gocher. You've switched the curvature there.
Right. Oh yeah. So I didn't. So I showed you how you can conformally rescale H3 times S1 to make it R4. You can do another scaling and make R4 into S4. So that's what they were doing here. They sort of did two conformal rescalings of space, and then you're looking, really it's a metric on the moduli space of instantons on S4. Does that answer the question?
Possibly, but S4 is not conformal to flat, so I'm not sure what it means. Or S4, yeah, S4. You've got to do something else. S3 cross R is a natural conformal metric on it, but I don't see S4.
Right, S3, oh yeah. Okay, S3 cross R is conformal as well. But yeah, that's yeah, okay. So what they did here, they conformally rescaled the underlying space to S4, and that broke some of the symmetry of hyperbolic space. That's all we really need to take away. Right, so I want to come back to this paper of Figueroa, O'Farrell, and Garanti. So they wanted to build up a supersymmetric gauge theory, which includes hyperbolic monopoles. And around that time, there were a few papers looking at supersymmetry on curved space-time. So this kind of fitted naturally into what was going on elsewhere. Anyway, but by writing down the supersymmetry algebra and the supersymmetry transformations, they came up with this new gauge fixing condition, which is different from the one we saw before. So the first two terms look the same: divergence of A, commutator of phi with phi, but there's this extra term plus or minus 2i phi. Okay, so the yeah, how this project started was I just wanted to look at that gauge fixing condition and see if it gives you anything nice as far as metrics go. And well, the answer is it does. So this is the main theorem in the paper with Guido. So what it says is you take a path in the moduli space of hyperbolic monopoles, and you get a little a and a little phi, and then the theorem says you can always make a gauge transformation so that little a and little phi solve that gauge fixing condition. And then the really surprising bit, the unexpected thing that occurred, is that if you do that, the integral that defines the metric becomes finite. So choosing this gauge fixing condition rather than the conventional one makes the divergence go away.
And what is the big difference between little a minus little a plus? You get the two gauge fixings both working, and then why do you separate that? Could you not just?
Yeah. Okay. So so I say it's a new gauge fixing condition. There's really two new gauge fixing conditions because you can choose the coefficient in front of the last term to be plus 2i or minus 2i. And so there will be one gauge transformation that solves the plus condition and another that solves the minus condition. And whichever one you choose, this integral will be finite.
But it's really two integrals.
Sorry?
It's really two integrals.
Yes. So yeah, it's two integrals.
They're both finite. Two different integrals.
Yes. Okay, but they're not unrelated. So right. The bottom line of the screen is hidden. Don't know how to fix that. So yeah, you have two different integrals. They're both finite. There's a g plus and a g minus. Well, it turns out g minus is just the conjugate of g plus, the complex conjugate. And okay, talking about complex conjugates, the price to pay in this theorem is no longer obvious that integral is going to give you a real number. So it's not obvious that this is really a metric. Although we'll see more about that in a moment.
Well, is that right? So you're saying that little g plus is the complex conjugate of little g minus.
Yes.
But if it's real, then
right. Yeah. Yes, but
you have to prove that.
Well, we'll come to is it real or not in a minute. Yeah, and the reason it's now complex is because there's an I in the equation at the top.
And so what's the dimension of the space here? 4n, what is n?
So n is, I'm not sure what it says for n. N is the dimension, n is the topological.
Yeah, so what is n for this metric? What's the dimension of the space this is a metric on?
Sorry?
What's the dimension of the space that this is a metric on?
Oh yeah, it's on a 4n dimensional space.
4n. Yeah. So could it be a Hermitian? Could it be a complex space?
We'll come back to that as well. Okay, so the first question is, the first question people often ask is, how does this evade the divergence? What's the trick? If you remember before, the problem with the divergence, it was to do with this integral, things being non-zero at rho equals 0 at the boundary of hyperbolic space. So what happens with this gauge fixing condition is on the boundary of hyperbolic space, it ensures that ax plus I times ay is 0, or in other words, ay is I times ax. So then the term that was causing the divergence before it was the integral at rho equals 0 of ax squared plus ay squared. But if one of them is I times the other, that's the integral of 0. So the thing that caused the divergence is 0, and that's, morally speaking, that's what makes it work. But there are lots of other things to worry about, as we were discussing. So
just a little bit of clarification needed. So you've got, for the rho equals 0 integral becomes 0 equals 0.
sorry?
The rho equals 0 integral becomes just a straight 0 equals 0.
Right.
But you've also got the AZ bar is equal to 0. Right. You see if you have it there.
Right, so the gauge fixing condition tells you AZ bar equals 0. A rho is not 0, but it's, well, sorry. A rho is 0, but it was 0 before as well.
So I'm a bit confused because it looks like both of them should be 0. But obviously that's not
Both of what should be 0.
obviously that misses.
Sorry, right, the first integral is at rho equals 0. The second is the integral as rho goes to 0.
So that's only true at rho equals 0.
Yes. Yeah. Okay, so we do need to worry about if this thing is real, about if it's non-zero, non-degenerate, before we can really think of it as symmetric. So here's where we are with reality, and because I was waffling so much, we'll have to do this a bit quickly. But so G minus is the conjugate of G plus. So what I can do is I can write down their difference and try to show it 0, and it comes very close to being 0. But their difference is the integral of a total derivative. So I can use Stokes' theorem, make that a boundary term. But the boundary term I'm left with, in general, it's not obviously 0. However, there are some cases where I can use a different argument to show that the metric is real. So if instead of thinking about the whole moduli space, let me think about smaller moduli space, the moduli space of monopoles that are invariant under inversion of hyperbolic space. So like a transformation that fixes a point and sends everything else. Right. So on that space, this integral gives you something real. So you do have a real G if you restrict attention to that space.
Is lambda 0 then?
Sorry?
Is lambda 0 then? In that one inversion.
Okay, yeah. I didn't do it that way, but I think lambda is not 0, but I mean the integral vanishes because it has a symmetry. You know, like if you integrate an odd function, you get 0. It's that kind of thing.
Right.
And there's another case where I know it's real on the moduli space of charge 1 monopoles. I know it's real there because we were able to calculate the metric on the moduli space in that case. And in fact, we're able to calculate some components of the metric for any charge n, not just for charge 1. So you want to calculate the metric, you have to first solve this linearized Bochum-Holden equation and gauge fixing condition. There's one really easy solution, where A is the covariant derivative of phi, and little phi is 0. So an easy calculation.
What are the superscripts in bracket 0 do?
Right. So well, that's just a label. So this is.
So I can ignore that.
You can ignore that.
Okay.
Yeah. So for this is a zero mode that describes exciting the internal phase of all of the monopoles. So I told you each monopole had an internal phase parameter. This is exciting those, and yeah, so I can work out the integral for that, and it's just 2 pi times n times p. Another integral we were able to do is, well, let me take, so x and y, those are the killing vectors that generate the isometry group of hyperbolic space. And I can take complex linear combinations of them and feed those into the monopole fields, and that magically gives me solutions of the linearized Bogomolny equation and gauge fixing. And again, we can do the integral for those solutions.
F being some kind of curvature.
Sorry?
F being some kind of curvature.
So F is that's the field strength tensor for the monopole.
Oh.
And dA phi is the covariant derivative.
So that's the same one you had written down before.
Yeah, that's the same F that we had before. So, I mean, what's going on here? The y is like a boost of hyperbolic space. The x is like a rotation of the hyperbolic space.
Yeah.
So this is a sort of, it's a real boost of the monopole combined with an imaginary rotation of the monopole. So for that combination,
it's a generic motion.
Sorry?
It's a generic motion.
Yes and no.
You could have more.
Right. I have to have the correct boost paired with the correct rotation.
Oh, okay. So they can.
So, yeah, I can't just take a boost without doing the maximum rotation.
Because then it wouldn't satisfy the linearized one.
Well, yeah, this would. I'd have to do something else. But the point here is we can do calculations, and then if you specialize those to n equals 1, it tells you exactly what the metric is. It's kind of, well, what you would expect is the metric on hyperbolic space and the metric on a surface.
The product metric with the factor.
Right.
Sorry, what are little n, little p here?
So P, that's the vacuum expectation value for phi. Sorry?
That's the magnitude of the exit infinity.
Yeah.
Yeah.
Okay. Well. So yeah, I think it is 3:30, so I could.
It's okay.
Yeah.
You can go on if you want.
Right. Okay. I think this is. Oh yeah. Make the last but one slide, I think. So yeah, this is this is sort of further mathematical structure of the moduli space. So we talked a bit about this metric. It does seem to be real. It does seem to be non-zero, at least in certain restricted settings. So, well, yeah. What I want to show you here, first of all, is so a bit more about where this gauge fixing condition comes from. So this is really going back to this supersymmetry paper of the Grau, Harland, and Garapti, explaining what was going on there. So they got the gauge fixing condition by thinking about bosonic zero modes and fermionic zero modes. So the bosonic zero modes, they're the ones we've been talking about, solve linearized Bogomolny plus gauge fixing. And the fermionic zero modes, well, those are the supersymmetric partners. And if you're working on hyperbolic space, the supersymmetry parameters are what are killing spinners. So a killing spinner is a spinner, in this case, a spinner on hyperbolic space, where it's not parallel, but it solves this equation here. It's known as the killing spinner equation. And the basic observation is that if you take a bosonic zero mode and pair it with a killing spinner, it produces a fermionic zero mode. And if you go the other way, take fermionic zero mode and a killing spinner, pair them together, you get a bosonic zero mode. And all of that algebra works only if you have this special gauge fixing condition. So that was where it came from.
But did that imply the gauge fixing condition, or was it just a kind of clever deduction given that starting point?
Well, okay, this is a chicken and egg question, I think. So what I think what they did was, I mean, I think they started at the bottom. They tried to make the transformation, the relation between fermionic and bosonic modes work, and they found it only worked if they modified the gauge fixing condition.
Yeah.
Okay, so what that does for the moduli space, it gives you a bit more of a mathematical structure on the moduli space. So
you're pairing the modular space with a spinner bundle. Is that what you're doing? In a fashion
roughly,
where the twisting of the two is into something nice for you. I'm not sure what it's doing.
Yeah, it's something like that. So, I mean, the equations there say that you can think of a bosonic zero mode, so that's a tangent vector. You can think of that as a product of a fermionic zero mode and one of these killing spinners. And the mathematical way to write that is that the tangent space is a tensor product of this space E of fermionic zero modes together with the space of killing spinners. Where the killing spinners, I mean, they just belong to hyperbolic space. They don't know about the monopole. The fermionic zero modes, they very much depend on the monopole. You change the monopole, you'll change the fermionic zero modes. So you have this nice sort of splitting of the tangent space. You can write it as a tensor product. And actually, again, because there's a plus and a minus, you have two nice splittings of the tangent space. So this is where our picture starts to coalesce with what Oliver Nash and other people had done before. So Nash has an equation that looks like that, but derived in twistor space. And what that relation gives you is it gives you these things called pluricomplex structures. So a pluricomplex structure is a two spheres worth of complex structures. It's a complex structure parameterized by this vector n in the two sphere with some extra technical conditions, which I don't remember. So that's kind of close to hyperkähler. If you take that equation, j squared is minus identity, expand it out, you'll see it recovers the relations that I, j, and k are squared to -1, but you don't get the final returning relation ij plus k. So this is not quite hyperkähler, it's something a little bit weaker. So those are, and then
it looks like you just have one complex structure there.
no, it's a family of complex structures that depends on this two-sphere parameter.
Sorry, it's one complex structure for each n.
Right. Yes.
But as you vary n, what does it? Where is n? N is depending on the coordinates of the manifold.
Well, n is just a parameter.
It's just a parameter.
Yes. So you have a family of complex structures.
Complex structures. Okay.
But
there is a single module. There is a single complex structure for the manifold.
No, there's
at any given n.
Yeah, for any given n, there's a single. Yes, that's right.
If I change n, I'm changing my coordinates. So it looks like it's still just one complex structure.
No, it's
But I can change the.
it is.
Well, I J and K are three different complex structures.
But JN is the only thing that squares to -1.
Yeah, but you're taking linear
No,
combination.
well, but for every single n, Jn squares to -1.
Um,
I is a different complex structure to K. So 1, 0, 0, and 0, 0, 1 are different complex structures.
Yes, yes.
they don't coexist at the same time.
Well,
my problem.
that's philosophical. Yeah, they are genuinely different. Anyway, what sort of falls out very quickly from our calculation is these metrics that we wrote down. They're compatible in the sort of natural way where if you take an eigenvector for J, so that's a whole, what's called the homomorphic tangent vector, that will be null for our metric. So
I suppose my problem is that it looks very much like CP3 is a family of complex structures into S2 over S4. It's an S2 of complex structures over S4, which gives you CP3. It looks the same, similar to that type of thing rather than
well, so yeah, if you think about CP3 is the twistor space for S4. So okay, well,
but I can think of it as a family of complex structures on S4, which isn't quite family complex structure, but the whole
yes,
together.
Yeah, I mean, the idea of twistor space. I mean, whenever you have a sphere of two complex structures, you have a twistor space, and the idea of the twistor space is you kind of add two extra dimensions to your manifold, and as you move around with those extra dimensions, you change the complex structure.
Exactly.
So yes, that's. I mean, this is similar, and there are twists. When you have a pluricomplex structure, there's always a twistor space, which knows about all the complex structures. Yeah, so there's compatibility, which is nice. So this is something like the closest we're going to get to the hyperkähler property. And okay, so lots of things that are ongoing. So with various collaborators, Guido Franchetti, Thomas Galvin, Lyndon Disney Hogg, we're trying to calculate the metric on the two monopole space. That would be nice. That would be a hyperbolic version of the Hitchin. With another collaborator, Marco Osala, I should stress everything we've done so far is for P half integer, so that a T is restriction. With Marco Osala, we're trying to relax that and make this work for any P. And there's lots of other stuff that I would like to be doing, but only have so much time. So looking at things like the sense conjectures, quantum dynamics, classical dynamics even, trying to nail down more precisely what this analogue of hyperkähler is, and also coming back to these asymptotic metrics, the hyperbolic tag map metrics. Anyway, that's more than enough. So thank you for all your questions, your interest.
Questions? Can I ask? I mean, in the analytic limit, you explained how the geodesics of the metric give you monopole motion. So that's physical. So those geodesics are physical things. Monopole projections.
Right. Okay. So I mean that's here you're asking about classical dynamics.
Yes. Yes.
Right. And I wrote classical dynamics with a question mark. So.
The question is a bit more specific than that. Later on, you have G plus and G minus. You have two different gauge conditions that give you two different metrics.
Right.
But the geodesics are giving you something physical, and the physics should be independent of the gauge condition. G plus
Sure.
and G minus are the same geodesics.
Well, I certainly don't know if they have the same geodesics, but even if they did, I couldn't say for sure that this is going to describe hyperbolic monopole motion. So. If you remember back Manton's approximation, his gauge fixing condition came from Gauss's law. It was just one of the equations of motion. This new gauge fixing condition it's not obviously just Gauss's law. It's very natural from the supersymmetry point of view, but from the point of view of classical motion, it looks a bit weird. So, I mean, I'm cautious. I wouldn't say these are going to really tell us about the classical dynamics of hyperbolic monopoles. I'm more optimistic about quantum dynamics. But I mean, another thing I didn't write down there I'd like to do is hook up with these people who've started doing genuine simulations of monopole dynamics and see if they can tell me anything about hyperbolic monopoles, because that would be the right way to work out what's the best way to study dynamics.
Very simply, you have radial symmetry in the xy plane, and then this is that gives you row both. And then you have the other coordinates. What if you took symmetry in both planes?
Ah, right.
Would you get hyperbolic vortices?
No, you get, well, okay, it depends what you do. Yeah, so one thing you can do, you can impose symmetry under the circle group that rotates both planes. And if you do that, you get, surprisingly, you get some, you do that to an instanton, and you end up with something that looks like a monopole with a singularity at the fixed point. So that's one thing. You can do one reduction. If you do two reductions, yeah, I can't remember. I don't think you get vortices. I think that the way to get vortices is slightly different. Yeah, the standard way to get vortices is, this was Witten's idea, you impose SO3 symmetry. That reduces self-dual Yang-Mills to vortices in hyperbolic space. Two circle symmetries, I can't remember what it gives you, but I'll look it up later.
So you weren't happy with the natural metric on hyperbolic space because the monopoles were accelerating and seemed to
Right, that was the
divergent velocities.
The Hitchin metric,
yeah,
predicts that, yes.
But that doesn't seem that unphysical to me.
You're happy for monopoles
to get more and to be traveling faster and faster as they separate.
Okay, so right. So there's, I mentioned this one paper from well, a couple of papers, Franchetti Ross and Gibbons Warnick. So they made an approximation where they take two well-separated monopoles and they think of them as just as particles carrying magnetic and scalar charge, and they wrote down the natural Lagrangian for their motion, and they interpreted it as a metric. In their calculation, there's no acceleration as they separate. So that they've done a...
Seems more unphysical. That seems more unphysical in a negative curvature space.
Maybe it depends what we mean by acceleration. Okay, I think you're thinking of anti-de Sitter space, maybe.
I'm thinking of negative curvature, a space of constant negative curvature, and trajectories divergent from one another.
Ah, yeah. I mean, right. But what I'm talking about is worse than that. So, so in hyperbolic space, I mean, you're right that if you you start with 2 points here and let them move apart and following geodesics in the hyperbolic trajectory. It looks they move apart from each other. Yes, that's the basic fact. But there's
Now you would time parameters.
their velocities, if you measure their velocity using the metric, their velocity is still constant. But what I was saying is they do this and the velocity increases. It's like they're gaining
It's a
energy.
physical acceleration.
Sorry?
It's a physical acceleration.
Yes, a physical acceleration. They're gaining kinetic energy.
Yes, it seems still natural, but they would be gaining some sort of, because they're separating from one another.
Right, but remember there's no force between them.
So there's no force, it's flat space. But
There's no force in hyperbolic space. So that I can measure their energy, and their energy doesn't depend on how far apart they are.
Just like an argument.
So let's thank you.
Thanks very much for explaining that stuff.
Okay, thank you.